Thank you very much. Let's clap for him. So our next speaker is ready. So you guys are interested in Starknet and Cairo. Godspower is here to do justice to it.
Thank you. Hello, everyone. Sorry for the technical issues. So, for the next 15 minutes or so, I'll giving you a breakdown of Starknet and how it works at the core. So, apart from the smart contract part, writing Cairo, a colleague of mine will be doing a a workshop on that tomorrow. Please make sure you attend. It will be impactful. But then I'll just be giving you a walkthrough of how Starknet works under the hood, right? So Godspower Eze. I'm a tutor and a contributor at Starknet Africa. I'm also a core engineer. I'm currently a Ethereum Protocol Fellow. So here's what we'll be talking about. We'll be talking about overview of rollups, a brief overview of rollups, what Starknet is, and then we'll break it into components and how it works individually. And then at the end, we'll do like a basic transaction flow, how a user sends a transaction, what happens, and what happens at the end. So a brief overview of what rollups are. So the idea of rollups comes from the fact that you need to scale Ethereum because the transaction fees are high, everything is high. So there are a couple of mechanisms. So they are like side chains, they are like Validium, but rollups is just one of the ways you can scale Ethereum. So what do rollups do? So from the name, you understand that what rollups do is that instead of having all the transactions sent to Ethereum, what they do is that they bundle it up, right? They bundle it up and send it as one, right? So they have less users, so they can just bundle it up and do some compression and bundling to make it cheaper. Then they send it to Ethereum. So that's like the idea of rollups generally. And also, she asked at the beginning if you know Starknet. So what the good thing about this talk is that if you're an engineer, you don't need to know Starknet to understand this talk. It just help you understand what happens at the core, right? So just listen, and I believe you get something out of it. So secondly, they depend on Ethereum for their security and their finality, which means that because of Ethereum is like the most decentralized and the most secure chain, literally not even hype, is the most decentralized and the most secure chain, they benefit from the security, right? So the ultimate finality, which is after they've told you that it is final on E2, L2, you could just, they would still have to finalize it on Ethereum for it to be final. So, yeah. So just two types of roll-ups. So with the first one we have optimistic roll-up. So from the name, you will understand that the way optimistic roll-up work is that when you send transaction to optimistic roll-ups, they process normally, they do their thing, they use their compilers and all. But the idea of optimistic roll-up is that at the point when they want to add the transaction to Ethereum, they are optimistic about every transaction sent, meaning that until it is proven false, they assume that these transactions are correct, right? So that's where the name optimistic comes in, because they're optimistic about every transaction. But then if you feel like something is not going right, you bring up something called a fraud proof, right? Then you start a back and forth to say, okay, I'm sure that these transactions are actually false, and then back and forth. And at the end, if you are able to prove that, you get like a fee, and the person who sent the wrong transaction is penalized, right? So that's the idea. And then ZK rollups use something called, they use like cryptographic proofs. So there are different kind of cryptographic proofs, like, but most ZK rollups or most rollups use zero knowledge proofs, right? And our speaker talked about ZKPs, so that's what it's all about. So what we're talking about today is Starknet, and Starknet is a type of ZK rollup. So what is Starknet? So Starknet falls under the class of ZK rollups, but then they like to call it validity rollup because of the way it works. So here's how Starknet works. You send a transaction to Starknet, it processes the transaction, you do your normal things like you're using a normal um, blockchain, but then what happens at the end is that they verify the process these transactions and they create proofs for it, right? So what is actually happening when they're about to add these transactions to Ethereum is that they are not rerunning it, they are validating that these transactions are actually real, right? So they like to call themselves validator. We call it validity rollup because they are not literally ZK rollup, because you're just validating. You're not doing anything new, right? So that's where the term comes from. And so we call Starknet a validity rollup, but you can just call it a ZK rollup if you want. So basically, the proof verification is cheaper than the online computation. So there are like some technical backup for this, but then just know that the way Starknet works compared to other ZK rollups, the proof size, proof verification is cheaper than the underlying computation. So the idea is that um, they have done the computation, so you don't have to do the computation, right? So what they do is that they do the computation, and instead of sending the computation, they give you a proof that they've done it, so you don't have to do it, right? So that's just the idea of having proof verification is cheaper, right? So a really good machine, right? A really good machine would do will create the proofs, and a lesser machine, like in some sense, will do the verification, meaning that you don't need to have as much computational power to do verification compared to actual computation, right? So it's more like um, compute once, verify like as long as you want. So it's based on stacks rather than snacks. So what this means is that the world of ZKP is really, really big, right? And there are different mechanisms, right? So Stacks is the one that was created by founders of Starknet, which is Eli Bensassin, and some other people. And then Snacks is actually much more older, but we currently use Stacks, and there are benefits of why they actually use Stacks. So one more technical detail, stack proofs are quantum secure. So there are like some technical backings to this, but just know that if a time comes where we have quantum computing, stack proofs are actually quantum secure. So now what we'll be doing is we would be going into it one by one, right? So we are breaking Starknet into components, right? So we'll talk about what each of these things do at the core: the sequencer, the prover, the full nodes, the verifier contract, and the core contract. So like I said, even if you don't know about Starknet or you've never heard about Starknet, these things are deep technical concepts that you don't really need to apply to Starknet for it to make sense. They are just computer science, and they make sense, right? So the sequencer. So the way this works is that this is supposed to be the entry point into the Starknet blockchain, right? So basically, how do a user send transaction into the blockchain? What part of Starknet does the user send the transaction to? So this is like the entry point. So basically, transactions are sent to the sequencer using gateway APIs or using full nodes. So as I said here, gateway APIs will soon be deprecated because based on the Starknet ecosystem is growing fast and they are making a lot of updates. So by design, gateway APIs will be deprecated soon, and you just have to use full nodes. And it's actually recommended because the way you use networks like Ethereum is that you use something like Infura, Alchemy, understand? So you just use these services rather than using like an API. So I feel like they are like security considerations. That's why they're actually deprecating this one, right? Um, so the blockchain in itself is like a computer, right? So that's why I said it contains the Starknet OS, right? So basically, the part of the blockchain that actually takes your Cairo code, processes it, turns it to something, and turns it to something is contained inside the sequencer. So the sequencer contains the Starknet OS, and it processes your transaction. And the sequencer is also responsible for creating blocks, right? So at the end, when I'm bringing everything together, I would show you how these things are done, right? I will tell you how these things are done, and then you would see how everything comes together, right? So, but for now, just understand that the sequencer creates blocks, right? It contains the OS, it does the transaction, and that's it. So then the prover. Now, the prover is a very critical component of any ZK rollup, because the idea of ZK rollups is that we create proofs, right? So from the name, you know that this is a part of the component, or this is the component that creates the proof, right? So if you say your core business is based on something, that particular thing that does that thing should be like the most important, right? So this part of the Starknet system is like the most important because this is where proofs are created, right? So basically, what they do is that when sequencer processes the transaction, nothing fancy, just processes the transaction, then gives it to the prover, right? So what the prover does is that it creates proofs of this transaction. Now, remember at the beginning, I said that you have to compute once so that I can verify multiple times, right? So what this prover does is that it takes those transactions in something called execution traces. You don't need to understand what they mean, but that's what they're actually taking. So the prover takes in execution traces and it creates proof of those transactions, right? So the prover is like there are different types. So the current one is called the stone prover. So this stone prover is like it's something that has been used internally by Starkware for like a very long time, but they will be open sourcing it soon. So if you're interested in things like that, you could like look into it and try to play with it. It'll be very hard, Pastor, but you can try it. So Lambda works. There's one built by Lambda class. Lambda works. It's still in development. And there's this one built by Sandstorm, a very smart guy. So there's this one built by this guy. And then there's another one called the Sharp Prover. So before they actually talked about Stone Prover for the first time, what most people knew was like this Sharp Prover. So what Sharp Prover does is that it's the name is from shared prover. So that's why it's like Sharp. So it's from shared prover. So what it does is that, from what I know, the sharp prover is like an infrastructure on top of the stone prover, right? So the stone prover have been closed source for a very long time, but they created the shared prover so you could use it without actually seeing what's happening inside of it. So this is what it does. So just to recap a bit, this part of of Starknet is what actually does the proving. It takes your transaction, it takes it as something it understands, like I said, execution traces, creates proofs, right? And then we'll actually see how these proofs are used. So now the full node. So the full node is not that shiny. We already know what full nodes do in the blockchain, right? Like on Ethereum, or you may know what it does in the blockchain, and it doesn't do anything new here. What it does is that it stores the state, right? So basically, as the transaction is sent to the sequencer, it kind of gets the current state. So it's more like it's always in the flow. So if you send a transaction, it knows what the transaction is doing. Is it received? Is it rejected? Is it pending? You understand? So that way they just stores the state, right? And um, these are a couple of them that are currently existing. So if you're into core engineering or you're interested in core engineering, you should actually look into these things, right? So there's Pathfinder written in Rust, Juno by um, Nethermind, and they're like Papyrus by Starkware and all. So yeah, you could look into this. So now we'll talk about the parts that actually have to do with Ethereum, right? So we talked about the prover, right? So once you hear the word prover, you should know that there's something that is verifying on the other end, right? So there's the prover, there's the verifier. This is the verifier. So the verifier is a contract on Ethereum, right? So now you would actually see everything coming together because when you talk about L2, right? If there's no part of the L2 that's talking to Ethereum, so it's probably not an L2, right? So this is the part where you see like how it actually works with Ethereum, right? So what it does is that the prover creates these proofs, right? And it sends it to the verifier contract. And the verifier verifies this proof, right? So that's what it does. It verifies this proof on Ethereum and make sure that it is real. Because the way it does is that it already has some existing information about Starknet, right? So when it takes this new proof, it checks, right? It checks whether this is actually correct, right? So that's what it does. And now if you remember what I said about optimistic rollups, now you don't need to have back and forth, right? You don't need to have fraud proof. Like any transaction that is verified, right? But in the case of optimistic rollups, you might have like back and forth. So it might even take days for something to actually be finalized, right? So that's why I think like ZK rollups are actually faster generally. So and yeah, so basically it's a contract, right? So basically, it just adds these proofs to the core contract, right? So you might just see it as two contracts interacting with themselves. So the verifier has its own, and the core contract has its own. So what it does is that the verifier maybe calls a function on the core contract to like add. You understand? So that's it. Then lastly, about the components, this is like the, will I say it's the brain? So what it does is that it stores the current state of Starknet. So now when you hear store, it doesn't literally store the state of Starknet, it just stores the current state, right? So in computer science, the idea of states, just like we have state X, right? And want to move to state Y, right? We probably will not store everything, but we just know that this is the new state, right? So that's how you should see it. If the contract was storing like the whole state of Starknet, then this probably, it would probably be so huge, right? So this is what it does. It stores the current state of Starknet, right? So it also stores the verified proofs, right? So just for record keeping sake, right? It just stores the proof and it stores the state. Now, lastly, let's talk about what will actually happen if you send a transaction. Now, what happens is that when you send a transaction, it goes into the sequencer. Like I said, the sequencer is the entry point, right? When you send a transaction, it goes into the sequencer. And this transaction is currently marked as not received, right? So if you use a, a scan like Stack Scan, so you know the way you have Ether Scan, you have the ones for Starknet. So Stack Scan, Voyager, right? So you have things like that. So what it does is that once you send a transaction to the sequencer, it is marked as not received, right? So because the sequencer doesn't know this transaction yet, right? So what it now does is that it takes this transaction, it checks for some basic things, right? So it checks, do you have enough gas, enough ETH to pay for this transaction, or in the future, if there's like a Starknet token that does the fee thing, so it check, do you have enough stack tokens? Yeah. So it checks that, right? And if it checks some basic things like, are you the caller? Like some basic things that you don't even need to go into what the code does, right? So when it checks those things, right, it now tells you, okay, it adds this transaction to the mempool, right? So if you know if you've learned about blockchain, you understand that the mempool is just like a waiting room for transactions, right? So it's more like a waiting room for transactions. So what it does is that it checks for these basic things, it marks this transaction as received, and it adds it to the mempool. So it has received this transaction, right? So it's now waiting to be added to a block. So what it does is that now, if you remember, this transaction is now tagged as received because now it has validated the basic things it needs to validate. Now it wants to process it, but it is in the waiting room because there were other transactions there probably, right? So what it does is that it now processes this transaction and adds it to a pending block. So what happens is that the pending block needs a couple of transactions. So there's like a threshold. So let's say that by design, each block is supposed to hold 10 transactions, right? So, but if the block has 5, you don't expect it to like tag it as complete. So what it does is it processes this transaction, it adds it to the pending block, right? So it keeps adding until it reaches its threshold, right? So once it adds these transactions to the block, that transaction is marked as pending, right? So if you remember, we actually moved from not received to received to pending, right? So it moves these transactions to the block, the pending block, and it says this transaction is now pending, right? So when it reaches its threshold, let's say we now have complete 10 transactions, right? What it does is that the sequencer creates something called the execution trace, right? So the execution trace is what the prover understands, right? The prover probably doesn't understand machine language or something like that, right? The prover understands execution trace, right? And from it, what on any computer software, any programming language, there's something called like a trace, right? It's more like like say a transition function or some code that actually lead you from where you started from. So basically, just like let's call it an output of a transaction. That's but nonce. Uh, maybe, but then just if toxin trace that's what the sharp prover understands, right? So it takes it into the prover creates the proof. So at this point, the transaction is marked as so at this point, transaction is marked as pending. Is that in that right? Full node, like I said, is always in the flow. It's always knowing, okay, what is this transaction? What's currently going on? It tells the full node that this transaction is happening, right? The full node know what is currently happening with this transaction. I tell people that are actually waiting for me what is happening, that this transaction is currently pending, right? If you now check what it now does, it sends the proof to the verifier, right? So what the verifier does is that if it is valid, like you're seeing here, it adds it to the Starknet core contract. So this smart contract on Ethereum. So what it does is that once the verifier verifies this transaction, it adds it to the contract, right? And then once it adds it to the core contract, if you see this flow back, it now tells the full node that this transaction is accepted on L2. So, okay, I did actually mention that once the transaction is in the pending block, it is marked as pending. And the transaction is sent, it's marked as accepted on, okay, it's marked as, right? So there's like 5 phases, like the not received, accepted on L2, which is Starknet, and then there's accepted on L1, which is the ultimate finality, right? So it's at this point you know that this transaction is not just it has not just finished on Starknet, it has also finished on Ethereum, right? So what it does is that at this point it tells them that this transaction is accepted on L2, right? So based on the way it's designed, you can actually use that as a source of truth. But if you're someone that, okay, I want this transaction to be finalized completely, you probably want to wait. Okay, a service like Binance, right, might want to say we are not satisfied with that. We want to see that the transaction actually finished. So they might wait till it's accepted on L1, right? So what it does is that after the stack verifies, it tells the full node this action is verified on L1. So accepted on L1. At this point, you can actually say that this transaction has been finalized, right? So I think I've been able to explain, right? So very much.
If you have a question, please you can ask for it. What's your Twitter? So definitely. OX Godspower. You can message him about everything you want to know about and about